Before 2022, a 128,000 token context window was physically impossible. Not impractical. Not expensive. Impossible. One attention layer at that length needs 32 gigabytes just for intermediate calculations. A full model needs 32 terabytes. Then flash attention showed up. 2 years later, models went from 2,000 token contexts to over 1 million. Same hardware. Same exact mathematical output. The trick wasn't a new model architecture. It was a smarter way to move data through the GPU's memory hierarchy. Here's the problem. Every token in a sequence has to score itself against every other token. That creates an attention matrix that grows with the square of the sequence length. At 1,000 tokens, the intermediate matrix is 2 megabytes, fine. At 8,000 tokens, it's 128 megabytes per layer. At 128,000 tokens, it's 32 gigabytes for a single attention layer. Now multiply by 32 layers and 32 heads. You get 32 terabytes. That's more memory than exists on any single GPU on the planet. And the frustrating part? Almost all of that memory is allocated to a temporary value that's used once and thrown away. To understand the fix, you need to understand how GPU memory works. There are two levels. HBM, that's the VRAM you think of, the 24 gigs on your RTX 4090. It's big, but slow. About 2 terabytes per second bandwidth. Then there's SRAM on-chip memory, right next to the compute cores. It's tiny, only about 20 megabytes on an A100, but it's 10 times faster at 20 terabytes per second. Standard attention makes 5 round trips to HBM per layer. It writes the giant n-by-n matrix to slow VRAM, reads it back for Softmax, writes again, reads for the value multiply, writes the final result. The GPU spends most of its time waiting on memory transfers, not doing actual computation. This is called the memory wall. Before flash attention, researchers attacked this problem by approximating the attention. Sparse attention dropped connections. Linear attention used kernel approximations. Low-rank methods lost detail. All of them traded accuracy for speed. Flash attention's authors asked a different question: what if we keep the exact same computation, but reorganize it so the n-by-n matrix never leaves the fast SRAM? This was the paradigm shift. Instead of making attention approximate, make it I/O aware. Pay attention to where data lives and how it moves. The output is mathematically identical to standard attention. Same numbers. Same result. Just computed with dramatically less data movement. The core mechanism is called tiling. You split the query, key, and value matrices into small blocks, chunks small enough to fit in at 20 megabytes of SRAM. Each block loads from HBM into SRAM exactly once. Then you compute all the attention operations inside the fast memory, the matrix multiply, the softmax scaling, the final output accumulation. The giant n-by-n matrix is never materialized as a whole. You only write the final result back to HBM. Instead of 5 round trips per layer, you get 1. Instead of quadratic memory, you get linear memory. The savings get larger as the sequence gets longer. Now here's where it gets clever. Softmax requires knowing the maximum value and the sum of exponentials across all elements. But with tiling, you only see one block at a time. So the authors invented online softmax. You keep 2 running variables, m for the maximum seen so far, and for the sum of exponentials. As each new block arrives, you compute the new max, rescale the old values to match, and update the running sum. The output from each block is correctly weighted by a rescaling factor that accounts for all previously processed blocks. When the last block finishes, every element has been properly normalized against the entire sequence. The result is mathematically identical to computing softmax on the full matrix. No approximation. No shortcuts. Flash attention 1 dropped in 2022. It was the breakthrough, 2 to 4 times faster than standard attention, and linear memory instead of quadratic. It proved the concept worked. Flash attention 2 came a year later, rewritten from scratch. It was 2 times faster than version 1 by parallelizing across the sequence length dimension and reducing non-matrix operations. On an A100, it hit 73% of theoretical maximum throughput, up from 30%. Then in 2024, Flash Attention 3 targeted the H100 Hopper architecture. It exploited new hardware features: asynchronous data movement, warp specialization, and FP8 precision. On Hopper GPUs, it hit 75% utilization at 740 teraflops, and over a petaflop with FP8. But here's the catch for local users: FA3 requires Hopper hardware. That means H100S and H200S. Your RTX 4090 is Ada Lovelace. FA2 is the best you'll get. The impact has been enormous. In 2020, GPT-3 had a 2000 token context. By 2024, Gemini 1.5 Pro hit over 1 million. Claude went to 200,000. Llama 3.1 supports 128,000. Qwen 2.5 pushed to 1 million tokens. This isn't a coincidence. Flash Attention is the common enabler. It's now baked into PyTorch's default attention function. Every PyTorch user gets it automatically. The applications it unlocked are real, analyzing entire codebases in one prompt, summarizing full books, understanding video across hundreds of frames, and building agent systems that remember entire conversations. Before Flash Attention, all of this was memory prohibitive. After, it became routine. If you run llama.cpp with CUDA, you're already using Flash Attention. It's enabled by default. This is why you can run a 7 billion parameter model with 32,000 token context on a 24 gig GPU. Without Flash Attention, that same setup would need 80 gigabytes just for attention intermediates. It simply wouldn't work. The biggest practical benefit for local users is prompt processing speed. At 32,000 tokens, Flash Attention processes the prompt about 5 times faster than standard attention. That first token latency, the time between hitting enter and getting a response, drops from seconds to milliseconds. For short contexts under 2,000 tokens, the benefit is smaller. But for long contexts, Flash Attention makes the difference between usable and impossible. Flash Attention is one of the most impactful machine learning papers of the 2020s. Over 4,000 citations. Integrated into every major framework. And it's not a new model architecture, it's an I/O-aware algorithm that computes exact attention with dramatically less memory traffic. The unsung hero of the local LLM revolution. Without it, running 128,000 token models on consumer GPUs would be physically impossible. If you've ever wondered how your local LLM handles a 50-page document in one shot, now you know. Subscribe for more AI infrastructure explainers, and drop a comment. What's the longest context you've actually used in practice?